Sometimes a matrix that we're interested in is related to a diagonal matrix, and we can use that relationship to take advantage of the fact that diagonal matrices are easy to work with. They're easy to multiply by, and it's easy to raise them to powers. So first of all, let's call matrices A and C similar if there is an invertible matrix S such that C equals S inverse AS. An important fact about similar matrices is that they have the same eigenvalues. And the reason that they do is that the eigenvalues of C are the solutions lambda to determinant of C minus lambda I equals 0. But determinant of C minus lambda I equals determinant of, let's see, C is S inverse AS minus lambda. I'm going to write I as S inverse S because it's true and it's going to help me simplify this expression. So this is the determinant of, let me pull out an S inverse on the left and an S on the right, and then I have A minus lambda I inside those parentheses. Now this is determinant of S inverse times determinant of A minus lambda I times determinant of S. Because determinant of this matrix times that matrix times the other matrix is just the product of the three determinants. Now since determinant of S inverse is 1 over determinant of S, and S is invertible so its determinant is not 0, determinant of S inverse and determinant of S cancel each other. So we have determinant of A minus lambda I. Now that is equal to determinant of C minus lambda I. So that means that the eigenvalues of C are just the eigenvalues of A. Now a fact I want to point out is that if we choose S so that jth column, well, if we have a basis of eigenvectors of A, let's say B equals V1 through Vn. And we define S by the jth column equals the jth eigenvector, then something nice happens. So for example, let's choose a matrix A that we looked at already. 1, 2, negative 2. We looked at this a couple of videos ago. 2, 1, negative 2, 0, 0, 1. and it has eigenvectors 1, 1, 1, 1, negative 1, 0, 1, 1, 0. Corresponding to eigenvalues 1, negative 1, and 3. So this eigenvector has eigenvalue 1, that one has eigenvalue negative 1, this one has eigenvalue 3. So let's define S to be exactly this matrix here if we erase all the parentheses. Alright, now I did S inverse on my own. I won't make you watch all the row operations, but I got 0, 0, 1, 1 half, negative 1 half, 0, and then 1 half, 1 half, negative 1. I computed that and I tested it to make sure I had the right inverse. So I multiplied them and I got the identity. Now A is similar to S inverse AS, which is 0, 0, 1, 1 half, negative 1 half, 0, 1 half, 1 half, negative 1, times A, which is 1, 2, negative 2, 2, 1, negative 2, 0, 0, 1, and then S, which is 1, 1, 1, 1, negative 1, 1, 1, 0, 0. So if we multiply this together, we've got 0, 0, 1 for the first row. 1 half minus 1 is negative 1 half. 1 minus a half is 1 half. Negative 1 plus 1 plus 0 is 0. 1 half plus 2 halves is 3 halves. 1 half plus, 1 plus 1 half is 3 halves. And then negative 1 minus 1 minus 1 is negative 3. So that's the product of these two matrices. Now we'll multiply these two and we'll get, alright, first row just becomes a third row, 1, 0, 0. And then negative 1 half plus a half is 0, plus 0 is 0. Negative 1 half minus 1 half is negative 1. Negative 1 half plus 1 half is 0. And 3 halves plus 3 halves is 3, minus 3 is 0. 3 halves minus 3 halves plus 0 is 0. And 3 halves plus 3 halves is 3, plus 0 is 3. So we got a diagonal matrix by multiplying these together. And that diagonal matrix has on, as diagonal entries, the eigenvalues of A. So A is similar to a diagonal matrix that has eigenvalues of A on it. So I claimed before that if two matrices are similar, they have the same eigenvalues. So we can see that, but I didn't say before that we would necessarily get a diagonal matrix with eigenvalues. But in fact, if we choose S to be a matrix whose columns are eigenvectors, this is going to happen, as long as those eigenvectors are linearly independent. So let's suppose A, which is an n by n matrix, has a set let's say B equals V1 through Vn of n linearly independent eigenvectors. With eigenvalues lambda 1 through lambda n. And let's define S by the jth column of S equals the jth eigenvector. Then S inverse AS is diagonal, and it has the eigenvalues of A on the diagonal. Now, surprisingly, this is very easy to prove. So let's define D to be this matrix. So it's diagonal and has the eigenvalues of A on it. Then SD, this matrix of eigenvectors, times D has columns, let's see, S is going to be first eigenvector, second eigenvector up to nth eigenvector. And then D is lambda 1, lambda 2 up to lambda n. So multiply these together. So we see that the first column ends up being lambda 1 times V1. And then the second column ends up being lambda 2 times V2. And the nth column is lambda n times Vn. But this matrix is, well, V1 is an eigenvector of A with eigenvalue lambda 1. So this is A times V1 in that first column, and A times V2 in the second column, etc. A times Vn in the nth column. So this is A times the matrix whose columns are eigenvectors. This is AS. So we just showed that SD equals AS. And since S is invertible, another way of saying this is that D equals S inverse AS. There we have it. S inverse AS equals D, this matrix of this diagonal matrix of eigenvalues. The end.